Okay, so fingers crossed. I hope that's working. Here we were last time. So we were talking about confusion of variables. And remember, confusion of variables is, ultimately kind of an obvious point, right? If you look at how a composition should be set up, obviously the name of the variable that comes out of the first function can't be the same as what went into the first function, so that can't be x. Of course, that would be silly. And so since what comes out of f cannot be called x, likewise what goes into g cannot be called x, right? So setting it up like so was just asking for trouble. Not that you can't work your way around it, but it's asking for trouble. So much easier instead to just not confuse your variables, rewrite g in terms of a different variable, y is a natural choice in this case, and then be as sloppy as you like, and the notation keeps track for you of what is plugged in where. It's just automatic, no problem. So that's where we left off, and I'm just going to point out that the same exact concern is there for multivariable functions, composition of multivariable functions. And it's a little bit harder to see it. It feels a little bit weirder. You're much more likely to make the mistake of thinking that you could write down the derivative matrix of f in terms of x and y and g in terms of x and y. And there's so much going on, and it's fairly complicated constructions or sophisticated ideas in play. You might just naturally forget to think about, wait a second, what do I plug in where? So even more valuable then to be careful and rewrite the function, the second function, in terms of a dummy variable that makes sense. So again, if what comes out of f, if you decide to call those u and v, well, then, that has to be what you write g in terms of. Right? So you take the exact same function g, just written now in terms of different dummy variables to match up with what's coming out of f. And then there is no confusion of variables issue left to be worried about. Just write that, derivative matrices multiply just like you normally would. Let's see here. So the first function f, here's its derivative matrix df. That acts first. Do make sure to be careful about on the right versus on the left. It's really easy to mess that up. And, oh my gosh, it's so dangerous. So heads up on that. F is the one that acts first. G is the one that acts second. So its derivative matrix goes second. Again, careful of the order. And then you just kind of multiply things out. And the one little thing you got to be careful with, and again, the notation will keep track of this for you. Right? But when you are ready to multiply this out, and it's up to you whether you do this either before you multiply, like I've done here, or maybe after you multiply if you prefer. I tend to like before a little better myself. But just don't forget what, for example, u is. This u right here, that's the first input variable to g. That means it's the first output variable from f. And that means that it's x squared plus y squared. And then likewise for the v, don't forget to plug in for that as well. Okay, you had a...
No, it was just like my question when you said that if the notation could keep track of the order, and then technically yes. It's the order of what's on the left and what's on the right. You just got to be really careful about it. The convenient thing is that when you write down the matrix form of the chain rule, written in terms of compositions, the one that's on the left in the composition is the one whose derivative matrix is on the left in the product. That's kind of nice, but it's sort of the opposite of the ordering on the diagram. It's on the right in the diagram. It's on the left in the algebra. Yeah. Okay. Now, here's where things get a little bit more weird. Confusion of variables is sort of an obvious setup problem, right? There are other kinds of setup problems. And it's based on the following. Let me go back a few pages. If you go back to, way back here, right? Ultimately, where did our chain rule come from? Our chain rule came from the fact that we were keeping track of how we were composing multivariable functions. We are composing multivariable functions. That's what all of our argument is based on. All of our arguments are based on the idea that what comes out of F is what goes into G, and that's how compositions work. So now we rephrased this subsequently in terms of intermediate variables. Sorry, stopped a little early. In terms of intermediate variables. And you can kind of, if you prefer, choose to think of, hey, look at the diagram. Look at the paths. And if you look at the paths, and for each path you get a term, then you get this other form of the chain rule, and that's nice. Right? But the subtext here, it's easy to forget, is that you can only use diagrams to generate chain rules if those diagrams are actually representative of a composition of functions. After all, that's where this came from in the first place. It came from literally the matrix form of the chain rule that came from composing two multivariable functions. So that is an asterisk. That's got to be, anytime you write down any one of these chain rules, you've got to be talking about an actual composition of multivariable functions. Now this is all good, fine and dandy, and you can see, for example, what comes out of the first. Well, for one thing, you can see there is, in fact, a first function, and there is, in fact, a second function. And, various sort of obvious observations about what happens when you compose, and what comes out of the first is what goes into the second, for example. But let's look at this diagram right here. Suppose this is the diagram representing maybe a bunch of equations that you were given. And side note, that's what's going to happen in this next example down here. We're going to see a bunch of equations. And for example, notice y1 is given as a function of x1 and x2. And you can go on through this list, and you keep looking at equation and corresponding little additions to the diagram, and you kind of piece it all together, and this is what you get. Now, can I look at this diagram here and start talking about paths and terms and making a chain rule just out of this diagram? And I say no, not really, not based on the way we've set things up in this course. That does not represent a composition of functions. And remember, everything that we know about the chain rule is resting on this one actual analysis that we did in terms of compositions and vector velocities and derivative matrices. Right? So I don't see how this is a composition of functions. What are the intermediate variables? Right, and just for humor value, I like to point out, let's look at partial of z1 with respect to x1. I claim that's not even clear what that means. Let's try to make sense out of this. z1, here's the equation in question, right? z1 appears to be a function of x1, y1, and y2. It would seem to suggest that I'm supposed to let x1 be a variable, but then hold the other input variables constant. But wait a second. If I am changing x1, how can I insist that y1 be constant? It doesn't make any sense. This does not come from a composition of functions. I am not playing by the rules. We do not have any way of treating this situation as it's written. Ever see the nasty problem there? Okay, so there is a way to work around on this. That's how I like to think about it anyway. I'm sure there are other ways to think about it. I feel like if I could cheat, I'm just going to say, let's pretend that there was a variable right there on the diagram. Well, then all would be good. Then I would have 3 intermediate variables that are functions of x1 and x2, and then I would have 2 eventual outputs that are functions of those same 3 intermediate variables, and that would be fine. So I would like to just be able to kind of insert a little variable right there, but I can't change any of the underlying math. Right? This is not a wishful thinking, I'm just going to change my algebra. So the way I can do that is say, look, that new variable right there, it's literally x1. And so you notice that's what I'm doing. Let me see if I can squeeze this on here a little bit better. There we go. This new variable I'm introducing, it is literally x1. Let me circle instead of... I want to call it x1 star just to distinguish it as a different variable, but it's morally x1. And then I just have to rewrite, for example, when I say z1 is a function of that new variable and y1 and y2, well, I just have to rewrite that z1 can't be a function of x1, it's a function of its mirror, its ghost, x1 star, like so. Now, have I really changed anything here? Not really. I mean, I've introduced a new variable, but it's not really that new. It's just the same as x1. This equation is exactly morally the same because z1 is still, that is x1. Nothing's actually changed. And yet I now have a diagram that doesn't have these this sort of nonsensical non-composition problem. So my diagram with this now inserted, it's a composition, right? I have a first function and a second function. I could write down the regular old chain rule. Let's now make sense out of the idea of what is the partial of z1 with respect to x1. There's z1. There's x1. There's going to be an x1 star term. There's going to be a y1 term. And there's going to be a, color choices, a y2 term. Boring. Regular old chain rule. Yes?
Did we introduce a new dimension with the x1 star? And relatively speaking, is it necessary? Just because we're applying with x1, you can get to z1 automatically. You don't need that intermediate step.
Yeah, so let me take the second part of your question first. It's necessary because once I've got that inserted, now this is literally a composition of functions and I can use the chain rule that I already have. If I didn't insert that, this is not a composition. I don't know what that is, but we don't have a chain rule for this. You see what I'm saying?
Yeah.
So that's why it's necessary. Now, is it legal? Did I change anything? And I guess kind of in some sense. But look, if z1 is x1 star plus y1 plus y2, but x1 star is x1, it's really the same equation. The actual values of z1 aren't going to change as a consequence of it. The actual values of any of the variables not really going to change as a consequence of this. So this is, I've basically tweaked and created a new model that describes all the same variables, but that obeys my rules. Is that cool? Yeah.
If we just please go back to the previous diagram.
Uh-huh.
Let's say, for example, there wasn't a line between x1 and z1.
Okay.
Would that be a composition?
Yeah, absolutely. That is totally fine. So let's just write that down. Yeah. If let me do this with if I.
So could we eliminate that, or technically?
Well, if so, in some hypothetical world that this is the question we were asked, then it's a composition, and these are the intermediate variables, and there's the x's give the y's gives the z's. Simple as that. That would be no problem, but that's not the question we were asked, right? And in particular, notice this is representative of the fact that within this equation, x1 it's there. Z1's formula is dependent on x1. So I really need that to represent that.
The question, what are the independent inputs here? We're trying to find x1 and...
This is a rhetorical question.
Okay.
The inputs to Z1 are not independent. Yeah. So this is just another way of saying this diagram's messed up, doesn't follow the rules. I don't know what's going on there. Yeah.
Okay.
Yeah. All right. So this is a nice little hack to fix this. Of course, you will notice, pretty easy to argue, that this partial of x1 star with respect to x1, pretty easy partial derivative, right? That's just 1. And so that factor just disappears. And then, boom, there you go. And all is well with the world. Okay, so heads up for that kind of problem. Okay, let's talk about second derivatives. Real quick procedural note. This is not in the book. I think that is very unfortunate. This material, it might not be in the book, but it is in your future. Right? Again, in my ancient history past, second major in physics, I did a lot of second derivatives with the chain rule. And I'm going to show you an example of one particular way that it comes up, and that is one of many. Right? And of course, I recognize that engineering is not the same as physics, but y'all are going to be doing a lot of physics, and this second derivative chain rule stuff is going to come up. It's hard to get away from. Another procedural note, not in the book, but it is on the content syllabus, and I want to remind y'all on the content syllabus for every row, right? Every row representing a section of the book. There's an excluded material, meaning stuff you can ignore out of the book, and there's an included material, meaning stuff that should have been in the book but isn't, and that you are responsible for. It is fair game for the course. So this is in the included material column for this section. Okay, so really the best way to see how this stuff works, I think, is just to dive in. Ultimately, the trick that makes it all work is this right here. We'll come back and see why after we kind of get our hands dirty. Let's just dive in. For dramatic purposes, I'm going to momentarily scratch this out, pretend you didn't see this. We'll uncover that soon. Okay, so question says, z is a function of x and y. Nice and regular, no issues of differentiability. R and theta are polar coordinates. And now flashback to whatever section that is. Polar coordinate, thank you. Polar coordinates is, that's where x and y are functions of r and theta, right? R cosine theta, r sine theta, right? So we have a composition here, right? The idea of taking some expression of x and y and reconceiving of it in terms of r and theta makes a composition. Okay, so the question is going to be how to compute the second partial of z with respect to r. That's a chain rule problem, but it's also a second derivative. And there's a sticky wicket. And in addition to the sticky wicket, there's a lot of details, right? So I'm going to go quickly through the details. Those details, if you, after class, if you pause the recording, think about it, you'll be able to follow. It's they're just little details, but there's so many of them. So just don't get snowed by all of the details here. Okay, so again, dive in. First step, we're going to compute the partial of z with respect to r. There's z, there's r, two paths, two terms, yawn. Notation. Now real quick, partial of z with respect to x, this is one of our notations for how to represent a partial. This is a different notation for representing the same partial. Likewise here. I didn't really do anything there. We'll see why in a second, why that's actually quite convenient. And then also, don't forget, we know polar coordinates. So we know how to take a partial derivative of x with respect to r. X is r cosine theta. You could just straight up punch out what these partials are. No big. All right, so we were asked, though, to compute the second partial with respect to r. So the r partial of the r partial. And now just to be clear what I'm plugging into what, there's our first r partial. And apparently I now need to take this first r partial and I need to take the r partial of that. Okay. Okay. There's usually a couple of little preliminary matters to take care of. Let's look at this term right here. We're taking a partial with respect to r. By the way, I love these diagrams. Don't try to do this without the diagrams. You will get lost. You will forget what's a function of what, what's an independent variable. There's so many things to keep track of, and the diagram does it for you. Let the diagram help you. Let the diagram be your guide, please. So if r is my variable, what that means is that theta is a constant. And if theta is a constant, that means sine theta and cosine theta are constants. And so we have here in this cosine theta, we have a multiplicative constant. Derivatives play very nicely with multiplicative constants. Those multiplicative constants just factor out. So just kind of convenient to get that out of the way before we have to really get down to business. Okay, and likewise, this also factors out. Okay, all right, now we have a problem. The problem is, what are we going to do about this thing right here? Partial of zx with respect to r. I'm going to first tell you the wrong way to do this, and by wrong way to do it, I mean I'm going to write down a bunch of garbage that students do a lot of times that has nothing to do with reality, right? And I like to show you what the garbage looks like so you know it when you see it and you don't accidentally do it yourself, right? So here's the garbage treatment of this. And that is to say, well, I've got z, and it says here I'm supposed to take the x partial, and then I'm supposed to take the r partial of that. So why don't I just write down zxr? What's wrong with that? Rhetorical question. So here's what's wrong with that. It suggests that z is a function of a set of variables that includes both x and r. It makes it look like z is a function of 4 input variables, and that is straight up not true. Now, I can view z as being the output from sort of my second multivariable function, in which case the inputs are x and y. Or I can view z as being the output of the composition, and as the output of the composition, the inputs are r and theta. Either of those is fine, but you can't say z is a function of these 4 independent variables because they're not independent, right? And you can see, in fact, if I were to try to do this, let's see here. Suppose I were to try to take the partial of z with respect to r here. Let's see here. Okay, so what did I decide? Z is dark blue. Let me start by taking the z partial of z with respect to r. So partial of z with respect to r would mean that's my variable. That means that these are supposed to be constant, and I have a bunch of nonsense. You can't fiddle with r, but insist that x and y are not allowed to change. X and y depend on r. You change r, you will be changing x and y. So this doesn't make any sense. That's just a bunch of nonsense. It's garbage. So heads up, don't write that down. That's bad. That's a bad look. Doesn't mean anything. Okay. All right. Now let me show you the right way to think about this. All right. The way I like to think about it, this is what I think is the right way to think about it. And this goes back up to what I skipped over at the very beginning. I made this observation that if z is a function of x and y, as indicated on my diagram, okay, well then its partials are also functions of x and y. We've made that observation before, and can and should be appended as such on the diagram. Zx is a function of x and y, and zy is a function of x and y. So just append your diagram. In fact, you'll notice where I have that written. I have it written right as soon as I finish writing down this line. I saw this ZX, and I thought, oh, better put ZX on my diagram. And likewise, ZY, okay, better put that on my diagram. So now, how do I make sense? Given our appended diagram, how do I make sense out of the partial of ZX with respect to R? Well, no sweat. There's the first path through X. That gives me the X term. Here's the second path through the intermediate variable Y. That gives me the Y term. And that partial is the sum of those two terms. It's just the chain rule applied to that composition, this sort of appended composition, this appended diagram with the ZX and the ZY just being explicitly listed. Paths, intermediate variables give paths, paths give terms. That's the chain rule. Everybody good? This is the nut of the whole matter. This is sort of what makes everything work, yeah.
So with the new appended, like ZX, ZY,
yeah.
How do you know that it goes through the X and Y output?
Yeah, so if, I mean, just, think by example, if Z is X squared, Y squared, so it's literally dependent on X and Y,
okay.
Right?
Yes.
Take the partial derivative, still allowed to be a function of X and Y. And even if, this issue comes up all the time, even if one of those factors kind of disappears, it doesn't matter if it is in the expression, the point is it's allowed to be in the expression.
I see what you're saying. Okay.
Yeah.
I don't really understand, since it's saying to take the partials in terms of R and theta, why don't we have any arrows going from theta?
Well, the question was to compute the partial with respect to, second partial with respect to R. Yeah, and so I'm computing the R partial now of what I've already previously computed as the R partial.
Okay.
Yeah.
It's just like the in terms of R and theta kind of like put me off.
Oh, so the partial is with respect to just R. In terms of means your answer is going to involve the following variables. Yeah. Right. Okay. So now, last details. By the way, again, this is the nut of the matter, right? Put your partials on your diagram. View their partials by way of the chain rule, just like we just did. And then, by the way, y'all can think through for yourself how this is that. Again, straight out of the diagram. Healthy exercise. I will point out it's really easy to forget extra stuff like the sine theta at the end. After all, look at all this algebra. Oh my gosh, it's a lot of stuff. Right? It's easy to kind of get that written and say, whew, wow, man, that was a lot of work, and then just kind of stop right there and forget that there is that extra factor. So everybody's got to deal with that in their own way. What has worked best for me over the years is to be very methodical in how I write these down. And I double check things as I go. And when I'm done with this, I go back to where it came from and it says, okay, now I'm done with that. What's next, right? And I don't allow myself to stop until I get all the way through. And the neater and more legible your writing and your spacing and your framing is, the less you will fail to read your own handwriting, right? And again, that's a thing. I've made that mistake plenty of times. So I know it just seems silly and undignified to have to worry about these little trivialities, but they will make a difference. So yeah, I hope that helps. Okay. All right, so it's all over with the shouting at this point. Again, there's no composition there. Z is directly a function of X and Y, and so there's no chain rule to be worried about. That's just ZXX, nothing to it. Likewise, there and there and there. And again, we have some explicit derivatives we can compute. There's nothing going on there. Don't forget about your extra factors here. And then you can take all of this monstrosity and kind of multiply, collect terms, and notice that it's a little bit more compact written as I have it at the bottom there. Yep.
I'm slightly confused. Well, you're saying ZXX instead of, like, I thought that was the notation we're doing for, like, saying it's a partial. So do you not actually have to find out the derivative? Or is that?
Well, we don't know what the function. I mean, we don't know how z is a function of x and y, so I can't.
Oh, okay.
I can't crank that out. Yeah, because I don't. In some sense, the whole point of this, you'll notice that this expression right here will be different depending on what different f's you have, right? And what this says down at the bottom is that the way you're going to compute that is by taking the function f that gives you your z and taking various partials, rectangular partials of it, and then combining those rectangular partials in this way. Yeah. Yeah.
This is also equivalent to just doing z of x cosine of theta plus z of y sine of theta squared. Like
I'm
the
sorry?
initial derivative, if you go back to the top, because remember you defined it as like
Yeah.
the derivative of z squared over dr squared. The initial derivative that we had.
Oh, yeah. This.
So
Yep.
is that a quicker way to like check it, or just
I don't understand what you're saying.
like could on the exam could you just do z of x, so like the first part, square it, and then that be your final product?
Oh, yeah. So this is another one of these unfortunate things about notation. This looks like squared. It's not. Yeah, this is annoying. This has always bugged me because it is confusing, right? And what you ask is a very natural interpretation of what's written here. But yeah, that does not mean multiply partial of. This is not a multiplication squared. This is an operational square. It means we're taking the r partial of the r partial. So yeah, it's tragic notation, but that's just not what that means. Yeah, I'm sorry about that. Yes. And this is going to have to be the last question. Go ahead.
Yeah. Could you quickly just go over the notation of like the subtext under this?
It's just this is just a notational alternative. You can go back in the notes to where we define partial derivatives. It's one of the first things we wrote down for how to what we mean by partial derivative. This is one notation. This is a different notation. That's all it is.
Okay.
Yeah, you can find it back in the Okay. Okay, so that's how you do second partials. Again, the key point is once the partials of this start to show up, like the zx and the zy, don't forget to append them to the diagram. And then everything else, you're going to notice everything else that we did in this question is stuff that y'all were perfectly capable of doing before today's lecture. It's just a matter of going slowly and carefully and thinking about what's a function of what and following paths and being careful about constants and stuff like that. Sometimes you have to use the product rule. I'll point out we got lucky this time that this product that we needed to take an r partial of, one of these factors happened to be a constant. That was a lucky break. You won't always get that lucky. Sometimes you'll have to write out the product rule before you can go on to the actual next chain rule step. So, but again, all that's kind of old news. Okay. Let me give you an example of why we care about this. I'm going to try to be as quick as I can about this. Turns out, for lots of very important physics and engineering reasons, I hope this is a persuasive list. For lots of really important reasons, we care about this thing called the Laplacian operator. The Laplacian operator is this thing right here. Notational observation. See how it's a little triangle? It looks a lot like the gradient triangle, except it's upside down instead of, it's pointing up instead of pointing down. Interpret that however you like. It's got to point the right direction. This means something very different from gradient. Okay. Anyway, so the Laplacian operator is a really big deal in physics, and turns out the Laplacian here can be rewritten in spherical coordinates like this. And I'll say a quick word about why momentarily. First, I want to recognize this does not seem to be a particularly helpful observation, right? Most students look at these two options and they're like, ooh, yeah, I think I'll take that one. right? Looks a lot nicer, right? It's not just you. It really does look a lot nicer. It's an illusion. Very often, this seeming monster down here is bonkers convenient, super easy. And I'm going to show you an explicit example later down the page where we can compute with this effortlessly. Okay. All right, but first I want to show you where it comes from. How do we get that? And it's just a matter of recognizing that when you have some function in rectangular coordinates in 3 dimensions, don't forget we have spherical coordinates. Spherical coordinates is a thing. X, Y, and Z are standard formulas from rho, phi, and theta. Right? So that's a function there. And so we have a composition. And so, for example, you can compute the second partial with respect to theta of f. You know, the second partial of that with respect to that by using methods just like on the previous page. I mean, morally equivalent. It's spherical instead of polar. A little bit uglier trig. There's 3 intermediate variables instead of 2, but ultimately it's pretty much the same thing. Same basic ideas will allow you to compute that. And what you'll get is some nasty expression, which, if you multiply by that, will give you a thing, which, if you add that in and then keep going and then take this and play the same game, and then you take this and you keep going, and when you add it all up, what you will find is that all of this together, horrifyingly inconvenient algebra. But if you do, you will get exactly that, as it turns out. By the way, I do not encourage you to do that yourself. It's not that you can't. It's that I don't think it's worth your time. And it would be quite a bit of time and quite a bit of algebra, and it's going to be this times 10. It's just a lot, right? So don't feel obligated to check that, but structurally and strategically, you see what's going on. It's just more of the same of what we have on the previous page. Okay, so who cares? How does this help us? And let's look at this question here. So this equation right here is very important. This is called Laplace's equation. No surprise, Laplacian operator. And it turns out that if you want to understand gravitational potentials and electric potentials, turns out they're mathematically very, very similar. Those functions have this feature that the Laplacian of those functions has to be 0. That's just how it works. Now, there's good reasons for that. This is physics. You take the appropriate physics class, and they will make very persuasive arguments as to why this equation should be true. But again, that's physics. This is not a physics class, so that's somebody else's problem. Okay, so now here's the thing. Our Laplacian. We have 2 different ways to write our Laplacian. The function that I claim works. Claim. Don't trust me. Right? But the function that I claim works. I can write it in spherical coordinates like that, or I can write it in rectangular coordinates like that. Now again, this is an easy conversion. This, almost a recopy. Right? So if you want to confirm whether or not you get 0 here, you have 2 different options of what to compute. You can compute this, you can compute that. Take your pick. Choose wisely. So most people pick this. Naively. First time. I did too. Don't feel bad. If you crank, and by the way, everyone should crank this out at least once in their lives. And I did mine. Turn. It's your turn. Okay, you do yours. And it's a pain because you gotta look. There's a fraction, and there's this exponent, and the square root, and oh my god, it's so annoying, right? It'll take you a page of algebra if you're efficient, and if you are not efficient, it might be more like 2 pages. So, you definitely can't do it in your head. This is a lot of work that goes into that. This one here, I'm going to do it in my head right now, and you are too. It's easy. It's easy. Promise. here we go. First step, let's look at this term right here. That term, apparently, the first thing I'm going to need to do is take a theta partial of this expression right here, which doesn't have any thetas in it. That's 0. Boop, gone. No thetas. Theta partial 0. Simple as that. Right? Sweet. Okay. So yeah, that term's gone. Okay, let's play the same game here. I'm going to have to apply that operator to this. The first part of which is I'm going to need to take the phi partial of something that has no phis in it. Gone. Poof. We're 2/3 of the way done. Everybody see how awesome this is? Is everybody coming around on the spherical Laplacian? Right? Pretty sweet. Okay, the last one, we're going to have to do a little bit of work. This isn't bad, though. A little bit of work. Let's look at this term right here. All right, I'm going to have to take the rho partial. There is a rho in here. Okay, fine. I'm going to have to actually take a derivative. The derivative of a constant over rho is a different constant over rho squared. So constant over, don't worry about the details, constant over rho squared, which we are then multiplying by rho squared, which makes this a constant, and therefore this derivative is 0. And that disappears, and poof, gone, done. Confirmed, we have a solution to Laplace's equation. Yes?
Why does, for the middle one,
Yeah.
do you have, what's the, like,
This one here?
plus symbol in that?
The what now?
Like, you have the symbol that you're taking the derivative.
Oh, phi.
Yeah.
Yeah, partial with respect to phi. That's right.
But isn't it sine of phi, so can't you?
Well, what this notation means is that I should take the phi partial first, and then when I'm done taking the phi partial, I should then multiply by sine phi, and I should then subsequently take the phi partial of all of that, and blah, blah, blah. But because that very first phi partial is 0, then I'm multiplying sine phi times 0, which makes this 0. And the phi partial of 0 is 0, and 0 divided by ugly is still 0. Does that make sense?
Yes.
Yeah. So when you're looking at a sort of a product of factors, of operators, then once you get 0, it's game over. Yeah, at least for that term. Yeah. Okay. So this is why we like the spherical Laplacian, and again, at a quick glance, most people are like pass, right? And most people are like, I'll do this one. But that's a terrible mistake. And so where did we get this lovely right here? Well, we got it by playing second derivative chain rule games, just like we did on the previous page in polar coordinates. All right, so fun example. Okay. All right. Okay. So y'all remember partial derivatives. I'm going to write down a bunch of stuff y'all already know about partial derivatives. Some of this is in a slightly different notation or phrased a little bit differently, but this is, I claim, all old news about partial derivatives. So partial derivatives are slopes of graphs. They're multiplicative factors, both with the asterisk that I'm moving in the direction of the variable with respect to which I'm taking the partial, right? So xi partial means that you're going in the ei direction. And by the way, I've made a point here of writing these directions by way of the unit vectors that point in that direction, not writing it in terms of the variable whose axis points in that direction. You'll see why in just a moment. Okay, so partial derivatives have those two interpretations. I claim you can rewrite the definition that we made of a partial derivative. You can rewrite that definition like this. It's just a matter of observing that because EI is a standard basis vector and it's mostly zeros, this actually creates a circumstance where only xi is changing, which is how you do partial derivatives. Right, now the details to think through, and that's a good exercise to try to persuade yourself. If you have any questions about why this works, come talk to me in office hours. Happy to help. But good argument to try to think through why this is just a rephrase of that definition. And then here's question.
So would it just be like the slope in the
Well, it's all of
in
these
the direction
things.
of the partial, not like.
I'm sorry?
So would it just be like the slope of the graph in the direction of the partial?
Well, so that is this interpretation. Yeah, that's right. But I'm making the observation that partials have lots of true facts about them. I'm enumerating true facts about partials right now. So you're absolutely right. It is the slope of the graph. It's also a multiplicative factor. It's also this thing. And it's also this dot product. Innocent observation. Again, easily checked. Crank out the right side here. Mostly zeros. You'll find that this is true also. Okay. So, again, key point. I've written all of this in terms of the unit vector that points in the direction that we're talking about. I wanted to write all this in terms of vectors. Unit vectors, not variables. Because, now let me go back to way long ago. Oh my gosh, this is all stretched out. Way long ago. Where am I? Here we go. Remember, we talked about what it means for a function to be a multivariable function. And to be a multivariable function, you have several input variables, like I've got written here. And I want to make a case that is really not the best way to think about, despite the name, right? The very common name, multivariable. Right? We shouldn't think of it that what goes into a function is a bunch of variables. It's much better to think about it that what goes into a function is an input point in the domain. Think of it as a single thing. It is, in fact, a single thing. It's a point in the domain that goes into the function. What we call variables are just the coordinates of that point with respect to your basis, whatever basis you've chosen. Okay, so with that in mind, let's look at this picture I've created here. And let me clean up the mess first. I should have done this earlier. Sorry, there we go. So what we have here is several level sets. Imagine this representing altitude as a function of location, like on a map. Like this is a mountain and this is uphill, right? And that's where I am right now. So which direction is the x-axis? I didn't draw the x-axis. Okay, which direction should be the x-axis? Not clear, right? I mean, maybe like this, right? But you could make the case for it looks like the map is actually more like this, and I'm just holding the map at a weird angle. Maybe the blue because of how the map is unfolded, but maybe the green because of how I've got it drawn on the page. Or maybe this is an arbitrary choice and there is no intrinsically natural way to do it. Choose whatever axes you like. It's all kind of arbitrary anyway. Okay, now with that in mind, let's suppose that for whatever reason we go with this, and then we're going to be like, okay, well then that's a standard basis vector, and that's a standard basis vector, and you see these are very special vectors because these are the unit vectors that point in the direction of our axes. And if someone were to come along and say, yeah, but I'm interested in what happens when I go in that direction, then we would say, oh, well, that's I don't know, that's a different, that's not a standard basis vector because you see our axes. And then the response would be, okay, well, yeah, but your axes were arbitrary, right? How about, I think we should use my axes, not your axes, and now your two green vectors are the ones that are sort of like weirdo directions, and now my vector is a standard basis vector, right? So, look, how you set up your axes and what are your standard basis vectors is actually pretty arbitrary when you're talking about a function. What we actually care about, right, what is intrinsic to the situation is if I'm at a certain point and I decide I want to start walking a certain direction, it's going to be a certain amount of steepness. And whether I call this a standard basis vector or not a standard basis vector, or how I set up my axes and what the coordinates tend to be based on whatever, man. How steep is it? Right? I'm tired. I would need to know how much pain I'm in for in having to climb this mountain. And I don't want to hear about all this coordinate nonsense. Right? So there's something intrinsic, and then there's something that's kind of arbitrary. So what I want to point out, and I guess we'll have to finish this up later, all of this stuff that I said about partial derivatives is based on the direction being defined by unit vectors that to now we've been thinking of as being special, because they're standard basis vectors, and standard basis vectors are special. And my big punchline here is going to be, they're not that special. They're not special at all. Any unit vector could be a standard basis vector if you set up your axes right. And so what we're going to do is we're going to take all these ideas and we're going to say, you know what, all these things that all work together, they work together for any unit vector. And we're going to define an idea based on that next time. All right, so see y'all later. Have a good one. I hope this recorded. Whoops.